Now we shall find the expression for the electric field due to an electric dipole at a point on the axial line. Now we consider an electric dipole, which is a system of 2-point charges which are opposite in nature and they are separated by a finite distance apart. So here we have 2-point charges minus q and plus q. Let O be the center of the dipole and A be a point in which the charge minus q is placed at, and B be a point in which the charge plus q is placed at. Now the distance between plus q and minus q from the center O is given by this small letter a. So this a is the distance of either charge from the center of the dipole. Now let P be a point on the axial line which is at a distance x from the center of the dipole. Now we want to find the electric field at this point due to this electric dipole. Now first we'll find the electric field due to a point charge which is plus q, which is placed at B. Now this electric field at P due to the point charge placed at B is given by 1 by 4 pi epsilon naught, then the q divided by the square of the distance of the point P from the point charge which is at B, and that distance is BP. So here we have EB to be equal to 1 by 4 pi epsilon naught Q by BP square. Now this BP, if you look at the diagram, this is equal to OP minus OB, and this OP is equal to X and OB is equal to A. So your BP will be equal to X minus A. Hence the electric field at point P due to the point charge placed at B, EB is equal to 1 by 4 pi epsilon naught Q. Instead of BP, we'll write X minus A. So here we have Q divided by X minus A whole thing square. So this is the magnitude of the electric field at point P due to the point charge placed at B. Now electric field is a vector quantity, hence the electric field EB has got a direction, and to find a direction we'll have to use one of the properties of electric field lines, which says that for a positive charge the electric field lines is directed away from the positive charge. Hence the direction of EB at point P will be away from the positive charge plus Q. Hence this EB will be directed along BP. Now there's another electric field which is due to the point charge minus Q placed at A, and the magnitude of this electric field due to the charge placed at A is given by 1 by 4 pi epsilon naught Q divided by the square of the distance between this point P and the charge placed at A, which is AP. Hence your EA will be equal to 1 by 4 pi epsilon naught Q divided by AP square. Now if you look at the diagram, your AP will be equal to AO plus OP, or OP plus OA, and OP is equal to X and OA is equal to A. Hence your AP is equal to X plus A. Therefore EA will be equal to 1 by 4 pi epsilon naught q. So instead of AP we have x plus a holding square. So this is the magnitude of the electric field at point P due to the point charge minus q placed at A. Now again this has got a direction, and using the properties of electric field lines, the electric field line for negative charge is directed towards the negative charge. Hence the direction of EA will be towards the negative charge minus Q. So the direction of EA will be along PA, or from P to A. Now the strength of the electric field due to the point charge at B will be greater than the strength of the electric field due to the point charge placed at A. Now this is because the distance BP is much more lesser than the distance AP. Hence EB will be greater than EA. And since at point P we have two electric field intensity, one is EA and one is EB, and since they are vector quantity, and you can see in the diagram that they are opposite to one another, so using vector rule of addition to find the resultant electric field intensity at point P, we'll have to take the difference between these two vector quantity EA and EB. And since EB is greater than EA in magnitude, the electric field intensity at point P will be given as EB minus EA. And we know that EB is equal to 1 by 4 pi epsilon naught Q by x minus A holding square, and EA is equal to 1 by 4 pi epsilon naught Q divided by x plus A holding square. So now we take common the Q by 4 pi epsilon naught. So we have here Q by 4 pi epsilon naught, then the 1 divided by x minus A holding square minus 1 divided by x plus A holding square. Now we shall take the LCM of this 1 by x minus A holding square minus 1 by x plus A holding square. So upon taking LCM, we'll have x plus A holding square minus x minus A holding square divided by x minus A holding square into x plus A holding square. Now these square in the denominator, we can take it common. So we have x minus A into x plus A, then take common the square. Now in the above numerator, we can expand it using the formula A plus B holding square. So here we have x square plus 2ax plus A square. Similarly, using A minus B holding square, what we'll get is minus x square minus 2ax plus A square. Now we'll open the bracket. Upon opening the bracket in the numerator, we'll get minus x square plus 2ax minus A square. Then we cancel x square and A square and this minus A square. X square minus x square, A square minus A square. So we're left with 2ax. Then in the denominator we have x minus A into x plus A. Again here we can use the mathematical formula A square minus B square, which is equal to A minus B into A plus B. So here this is the reverse. We have x minus A into x plus A will be equal to x square minus A square. So in the denominator you will get x square minus A square holding square. Then we bring q in the inside the expression. So E is equal to 1 by 4 pi epsilon naught to q2ax divided by x square minus a square holding square. Now if you can recall, q2a, this is the expression for the electric dipole moment P. So here we have, instead of q to a, we'll write it as P. So your E will be equal to 1 by 4 pi epsilon naught 2px divided by x square minus a square holding square. So that is the expression for the electric field intensity at point P due to an electric dipole on the axial line. Now since electric field is a vector quantity, so here your E also must be expressed in vector form, and the direction of this electric field E at point P is away from the positive charge plus Q, or if you can see the electric field lines of the electric dipole, you can see that it is directed away from positive Q and towards the negative charge minus Q. And to express in vector form, we'll have to express the dipole moment also in vector form. Now direction of the dipole moment is from minus Q to plus Q. Hence you can see that the electric field and the electric dipole moment is in the same direction. So in vector form, your E will be equal to E vector is equal to 1 by 4 pi epsilon naught to P vector x divided by x square minus a square holding square. So since they are in the same direction, we have E vector to be in the same direction as the P vector. So this is the expression in vector form. Now for a short dipole, that is when the distance a, or the dipole length, is very small as compared to the distance x. So for a short dipole, we'll have to neglect this quantity a. So here your E vector will be equal to 1 by 4 pi epsilon naught 2p vector x divided by x square. Neglecting this a, we'll get simply x square holding square, and here we have opening the bracket, you'll get x to the power 4. Then we cancel the 1x in the numerator and 1x in the denominator. You'll get x to the power 3 in the denominator. So for a short dipole, the electric field intensity is equal to 1 by 4 pi epsilon naught 2p vector divided by x cube.